The next chapter, angle properties of a circle. Now before I proceed, I need to say that in this video we will look at 9 rules, and as I will be making mention of it, 3 rules are supposed to be covered in Form 3. But I decided we do a holistic view of all of them because I also appreciate that some of you will be watching this video while you are already in Form 3 and Form 4. Believe me, it will do you a lot of good if we do it this way. Permission granted? Thank you. Let's get on it. We start with parts of a circle. Now this is a circle, a line that curves and joins with itself such that all points on the line are equal distances from a fixed point. That fixed point is the center, conventionally labeled as O. The length of the curvature is called the circumference of the circle. A line drawn from the center to any point on the circumference is the radius of the circle. If a line joins 2 points on the circumference and passes through the center, it is called the diameter. And so the diameter is twice the radius of a circle. A line joining 2 points on the circumference is called a chord. A chord divides the circle into 2 segments. The larger segment is a major segment and the smaller one is a minor segment. In view of this, a diameter is actually a chord that passes through the center. The segments formed by a diameter are called semicircles. An arc is simply a part of the circumference. So the curve PQR is a minor arc and PSQ is a major arc. The area enclosed by 2 radii and an arc is called a sector. So the region marked M is a minor sector and N is a major sector. When the chord cuts through the circumference, it's called a secant. A tangent is a line that passes outside the circle and touches the circle at only one point. So it's like the circle is standing on the tangent line. This information is important because we will meet these terminologies over and over in the chapter. From time to time, you may want to pause, rewind and replay the video if you feel the need to. So let's get started with our first rule. Rule 1. Now in this case we have an arc, and from this arc we have different points. In this case, the lines are crossing over and connect at the sides. Now the 2 angles at each point are equal. These angles are subtended by the same arc and are equal to each other. To be able to see them clearly, it is easier if you draw a chord here. We say these angles are subtended by the same chord on the circumference. That means if you draw another chord here, these 2 angles will be equal. Notice that the angles are in the same segment. The rule is, angles subtended by the same arc on the circumference are equal. We can write this in shorthand. Now I've said that the chord may or may not be drawn, and it is easier to see the angles if you draw the chord. So this rule can also be angles subtended by the same chord on the circumference of the circle in the same segment are equal. Let's take an example. Now in this example, we have a slightly more confusing pattern, but you can still see the lines crossing and connecting on the sides. This angle 50 degrees is subtended by this chord AB. This time we are lucky the chord is drawn. You can also see the angle is subtended by the arc ACB, but I always think it is easier to see the angle using chords. Draw the chord if it is not there. So this chord also subtends the other angle here, so it must also be 50 degrees. If we had a chord connecting DE, we can now see 2 of the angles subtended by that chord BD, or the arc BFD if you like. So if we had 80 degrees here, this angle here will also be 80 degrees because both are subtended by the same chord. Rule number 2, we have again a similar arc. We can draw a chord. This time we have 2 radii from the arc and another pair of lines from the arc to the circumference. This arc has subtended one angle at the center and another on the circumference. The rule is the angle at the center of the circle is twice as big as the angle on the circumference. So if this is A, this angle at the center will be 2A. So the angle subtended at the center by a chord or an arc is twice the angle subtended by the same arc or chord on the circumference of a circle. In short, we write angle at the center. So if we knew this was 30 degrees, what will be the angle here? It will be twice as big, that is 60 degrees. If it was 40, that will be 80 degrees. This rule is simple enough, but no examiner will of course give such a direct diagram. It is often drawn in a way that looks confusing. Another way it can be drawn, you have the same arc and chord and the 2 radii, but now you have straight lines meeting like this. At first sight it looks different, but it is in fact the same thing. The angle at the center is twice that on the circumference. So if this is 90, the angle outside will be half of that. It has to be 45 degrees. Another example, same figure with 2 radii, but the outside angle looks like this. These lines are crossing now, but it is the same principle. One angle at the center and another on the arc, both from the same chord. This is A, this is 2A. If A is 25 degrees, this will be 50 degrees. The final way is the most complex one. We have the same circle and radii, but now the outside angle is formed here. Trust me, it has the same rule. We still have our A, the angle outside, and the angle at the center is still twice as big. But be careful, it is the angle around the top this time that will be twice as big. Before, we had the angle at the bottom when it came to the circumference, and we had the equivalent angle at the bottom when we looked at the center of the circle. But here, the angle on the circumference is on the top of the lines, so our angle at the center is also on top as well. Be very aware of making the mistake of taking the angle on the inside, because this is a very popular mistake. So if this was 300 degrees, using the same rule, this angle will be half of that. It will be 150 degrees. Hopefully you can see the same rule in all these 4 examples. Rule 3. This is a diameter and 2 semicircles. If this diameter subtends an angle on the circumference, that angle will always be 90 degrees. And if you think about it, this is the same as rule 2. Imagine AO and OB to be 2 radii. They subtend an angle at the center of 180 degrees, that is angles on a straight line. So the angle at the circumference is half of that, 90 degrees. Don't you just love maths? So many things can be said to mean one same thing. So the rule is, the angle subtended by the diameter on the circumference is 90 degrees. You can also say, the angle in a semicircle is 90 degrees. In shorthand, it's angles in a semicircle. And it doesn't really matter where the angle is subtended. Either way, it is 90 degrees. Rule 4. This one deals with the tangent, and this should have been covered in Form 3, but let's do it here. If we draw a line from the center to the point where the tangent touches the circle, they will form a perfect right angle. And the rule is, a line through the center of a circle meets the tangent to the circle on the circumference at right angles. Again, it doesn't really matter where the tangent is. In shorthand, you can write radius is perpendicular to tangent. Looking at a slightly more complex example, now we have so much in the circle, but above here is the tangent. At its point of contact with the circle, we have a line going through the center of the circle. And so we know that the angle is 90 degrees, actually on both sides. Rule 5, this again is about tangent, but this time we have two tangents. Both come from the same point. If they come from the same point and both touch the circle, then the distance from their point of origin to where they touch the circle is exactly the same. The red lines are equal. This is quite useful for two reasons. One, it makes an isosceles triangle, and from this fact we can know that the base angles are equal. 2, if we had two lines going to the center from these points, we know these angles are 90 degrees from the previous rule. Knowing that these two lengths are the same, we can use the isosceles rule and combine with the previous rule we learned, that is the radius and tangent are perpendicular to each other. The rule is, two common tangents to a circle are equal. They will also have the same angles. In another example, two tangents from the same points to a circle, and there's a line connecting them. So you notice it's an isosceles triangle. If this angle was 70 degrees, we can work out the other angles. First, you know that the interior angles of a triangle add up to 180 degrees. And secondly, we know that we have an isosceles triangle with the same base angles. We already have 70. The base angles will share the remaining 110 degrees equally, and that makes it 55 degrees. Rule 6. In this rule, we have a circumscribed triangle, and we add a tangent. That tangent touches the circle at the exact same point where one vertex of the triangle is. The rule says that the angle between the tangent and one line of the triangle will be equal to the opposite interior angle of the triangle, which means this angle down here will be equal to this opposite interior angle. Just to put some numbers in there, if we had 75 degrees down here, we would automatically know that this angle here is 75 degrees. And you notice that the 75 degrees angle lines at the bottom do not touch the 75 degrees angle lines anywhere. If this is 53 degrees, you will know that this opposite interior angle is also 53 degrees. The rule is, the angle between a chord and a tangent equals to the interior opposite angles in the alternate segment. In shorthand, it's angles in alternate segments. For an example, here's a triangle and we have a tangent touching one of those corners. If this angle is 82 degrees, surely we can calculate x. Because you notice that this 82 degrees is opposite to angle x, and therefore they must be equal. X is 82 degrees then. Next, rule 7, we look at radii. Now, no matter where the radius meets the circumference, it's always the same length. If it wasn't the same length, it wouldn't be a perfect circle. So all these radii are the same length. And noticing that they are equal, if we draw chords to meet the radii, we form triangles. And not only that, the triangles are actually isosceles, and therefore the base angles must be equal. In the same way, this other triangle has base angles that are equal as well. So there is our rule. Putting some numbers, if this base angle was 60 degrees, you will know that the other angle at the base of the triangle is also 60 degrees. If this was 40 degrees, then this is 40 degrees as well. You could even work the final angles of the triangles, knowing that the interior angles sum up to 180 degrees. So the rule is, any chord that forms an isosceles triangle with the center must have equal base angles. In shorthand, you can write angles being the sum of the isosceles triangle, or you could just say base angles of an isosceles triangle. Looking at another example, this is a triangle with two radii, so it's isosceles. If the base angle was 20 degrees, we can find x. We know that the other base angle is also 20 degrees. The sum of interior angles of a triangle is 180 degrees. So our x is 180 minus 40, and that gives us 140 degrees. Rule number 8. This deals with a cyclic quadrilateral, a four-sided shape circumscribed by a circle. All the four vertices must touch the circumference. The rule is, the opposite angles of this cyclic quadrilateral are supplementary, that is, they add up to 180 degrees. So if I told you that this angle is 110, you would work out this angle here. It is 70 degrees. Or if I told you that this angle is 85 degrees, you could work out the bottom angle. Because you know it is the opposite angle, it must be 95 degrees. So the opposite angles of a cyclic quadrilateral are supplementary. In shorthand, you can say opposite angles of a cyclic quadrilateral. Looking at an example here, if I told you that this angle is 42 degrees, you can surely work out x. The two angles are supplementary because it is a cyclic quadrilateral, so x must be 138 degrees. Finally, the last rule, rule number 9. This is very similar to rule 8. It talks about cyclic quadrilateral, and we just learned that opposite angles are supplementary. Now, if we extend this one side, you notice that it makes a straight line. And we know that angles on a straight line add up to 180 degrees. So this angle here must be 75 degrees. But certainly, you can see that the 75 degrees we started with is equal to the 75 degrees we found in the end. And so we can remove this 105 degrees and see the two 75 degrees angles. That is, the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. You can write that in shorthand as exterior angles of a cyclic quadrilateral. If you look at this question, we have 143 degrees as the exterior angle of this cyclic quadrilateral. It follows that x is also 143 degrees because it is interior opposite to the angle 143 degrees. And so what have we learned? Let's recap the rules. The first rule, we said that angles in the same arc are equal, or angles subtended by the same arc or chord are equal. Second rule was that the angle at the center is equal to twice the angle at the circumference if both are subtended by the same arc or chord. Rule number 3, the angles in a semicircle or subtended by the diameter on the circumference of a circle are 90 degrees. Rule number 4, a tangent to a circle is perpendicular to any line that passes through the center of the circle. Rule number 5, two common tangents are equal. Rule number 6, the angle between a chord, which is part of a cyclic triangle, and a tangent is equal to the interior opposite angle of the triangle. Rule number 7, a triangle formed between a chord and two radii is isosceles with equal base angles. Rule number 8, the opposite angles in a cyclic quadrilateral are supplementary. And rule number 9, the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle of the figure. Now, so far we are good. The next part is to put our knowledge of these rules in practice in an exam question. An important thing is that no single rule works independently or in isolation. The same exam problem can be solved using more than one of the rules. We take two examples. Now, in this question, the line DAC is a tangent to the circle of center O. We are required to calculate the angle DAB and giving reasons for each step. Now in an exam, you need to write your answer and give reasons for it. Otherwise, you'll only score half the marks, even if the answers are correct. So the first angle we can see is CAO, and that is 90 degrees, because it is between a radius and a tangent. So CAO is equal to 90 degrees. Reason being, radius is perpendicular to tangent. Next, we know that interior angles of a triangle add up to 180 degrees. So we have that AOC is equal to 58 degrees because of the sum of interior angles of a triangle add up to 180 degrees. Next, we can note that BOC is a straight line at O. It forms an angle of 180 degrees at O. We already have 58 degrees, and so the remaining angle is 122 degrees. So angle AOB is equal to 122 degrees because they make angles on a straight line. Next thing, notice we have two radii BO and OA and a chord AB completing an isosceles triangle. So the base angles are equal. From 180 degrees, that is the sum angles of a triangle, we already have 122 degrees, and so the remaining is 58 degrees. If you divide that by 2, that makes it 29, because they are the base angles of an isosceles triangle. Finally, we can get our answer. DAC is a tangent and OA is a radius. They make an angle of 90 degrees. We already have 29 degrees, and so the remaining angle is 61 degrees. Reason, radius is perpendicular to tangent. Final example, and this is a funny one. We are given x instead of a number, and we are supposed to calculate angle ACB in terms of x. It is not hard as you may be imagining. As long as you know the rules, you can work it out. Let's start. AO and CO are radii, and so they form an isosceles triangle with chord AC. So the base angles are equal. So angle ACO is equal to x. Why? Because they are the base angles of an isosceles triangle. Again, AOC is a triangle and the sum of interior angles add up to 180 degrees. We already have x and another x. So what is remaining is 180 minus 2x. Reason? They are the sum angles of a triangle. We can now calculate the reflex angle AOC. Angles at a point add up to 360 degrees. We already have the obtuse angle of 180 minus 2x. The remaining is 360 minus 180 minus 2x. That should give us 180 plus 2x. Now, the chord AC has subtended the reflex angle AOC, the outside angle, at the center. And the same chord has subtended the angle ABC on the circumference. The angle at the circumference is half that at the center. And so we have a half times 180 plus 2x, and that gives us 90 plus x. The next thing we see is the pair of parallel lines. This angle x here is alternate to angle CAB, so they are equal. Finally, ABC is a triangle. Sum of angles is 180 degrees. We already have x and 90 plus x. So what is remaining? We have 180 minus x plus 90 plus x, and that gives us 90 minus 2x. Good luck with angles.
If you want to go on and major in math or do honors in math or do a career in math, you really do need to be good at it. But I think too many people stop out too soon because they've had bad experiences. I think math teachers have a lot of responsibility for that. We haven't taught it so well. We haven't provided the resources that people need. And so I think if you need help, you need to get it, and you need to get it early. And you need to work at it.